Good afternoon, and thank you for kind introduction, and thanks to ILSI for inviting me for this talk. Today I'll talk about the radio frequency processing. First, let me introduce what that is. It is an electromagnetic dielectric heating. Typically, you use around 27 megahertz, and it generates heats primarily by ionic conductivity and bipolar orientation. So when the electromagnetic waves are changing polarity like a 27 million times a second, and you have millions of water molecules and the ionic molecules, they vibrate, and the friction causes the volumetric heating. So that is the reason for more volumetric heating. When you compare to the traditional heating, the heat flows from outside to inside. The cold spot is the geometric center. So validation is relatively easy, right? Whereas in the RF processing, it's a volumetric heating, but still there are hot and the cold spots, and the cold spots may not be always at the geometric center. So that is the additional challenge it provides. Since all of you know about the microwave processing, I want to compare with the microwave. The microwave is a higher frequency. That means the wavelength is like 12 centimeters. So it interferes and creates a lot of hot and cold spots inside a microwave cavity. Whereas in a radio frequency, the wavelength is of the order of the football's field, 100 yards or so. Because of that, your electric field lines are almost parallel. Because of that, the heating uniformity is much better. And the penetration depth is also much higher in the radio frequency. So in an industrial setting, if you have a bed of a product going between the two electrodes, you can have a deeper bed. Whereas in a microwave, typically you try to keep it less than an inch thickness. The another important thing here is, let me use the mouse, okay, here it is. So the radio frequency region falls in vibrating the bound water, whereas the microwave is more vibrating the free water. So the radio frequency is a lot more suitable for the low moisture foods. That's why it's commonly used in the low moisture food products, whereas the microwave is more for the high moisture food products in general. The main advantage of the RF heating is the shorter come-up time. Because of the volumetric heating, it heats a lot more uniformly when compared to the traditional thermal processing. In a low moisture food product, the thermal conductivity is low too. It takes a much longer time to reach the desired temperature, whereas in a radio frequency, you can reach the temperature pretty quick. That's the major advantage of the RF. Because of the shorter come-up time, you could push towards the high temperature short time processing to achieve the same lethality requirement, and that would preserve you a much higher food quality. So that's the advantage RF provides. The other advantages are that it can be turned on and off instantly, and you can package the product. You need to select the package material carefully, and it's a lot more energy efficient. So those are the advantages. One another thing we need to understand is it's similar to microwave. If you put it in the RF, if the RF is on, it will continue to heat. So once you reach the desired temperature, either you have to cycle on and off, or it might be much cheaper to move it to the hot air tunnel or the oven for the holding time to achieve the desired lethality, and then you take it off. And the mechanism of the inactivation is primarily the thermal effect. There are few papers that claims non-thermal effect that you can consider it as a factor of safety, but the general consensus, it's purely thermal. So let me go over how we would develop a RF process for a given application. First, what you would do is determine the D and the Z values for your surrogates and the pathogen cocktail, and make sure you select the right cocktail, the right surrogate. And based on the D and the Z values, you pick the few time temperature combinations, and the goal is to push the temperature as high as you can without affecting the quality. So you go and then check the quick quality analysis to make sure you are not burning it down or separating the oil or changing the color dramatically. Once you finalize, narrow down the time temperature you want to use it for your pilot scale, the next step is to use the modeling. The purpose of the modeling is to identify the cold spots, where the cold spots are, because it's not always at the geometric center, and also optimize the package shape and the electrode shape to improve the heating uniformity for your product configuration. Once you do that, then you go to the validation. The validation, because it's purely a thermal processing, you can just follow the same methodology you would use it for a typical thermal process validation. You may put the inoculated product on like a cloth sachet, and then you put it in the cold spot area, and then you run it through the process, and then you make sure you kill all the bacteria. And finally, once you narrow down, the food industry is going to adopt only if the quality is good, right? So you do need to evaluate the food quality on those final conditions to narrow down the final process condition. So let me go through those steps quickly. So in the D and the Z value determination, because it's purely thermal, in the low moisture, we either use like a metallic discs, thin discs where we put the low moisture food product, put it on a water bath or the oil bath, and determine the D values at multiple temperatures. Or you can put it on like an aluminum sachet, put it between the dry blocks, and heat on the both sides at the same temperatures, and then determine the D values of the multiple isothermal conditions, and then determine the Z values. Then you look at the quick quality analysis. Then you go to the modeling. The modeling, it's primarily to identify the cold spots and the non-uniformity of the heating. That depends on the composition of the food, the shape of the food. That's a big effect. If there are sharp corners, they would attract the radio frequency field. It can even arc. The frequency, there are only 3 main frequencies are allowed by the FCC, so you have only few selections. And then you could change the electrode and the packaging design and the time for the treatment. So here is an example. So by changing the little bit of a shape, you can see that like the temperature difference can be dramatically minimized. The sharper edges, the temperature can go pretty high, while most of the things are low temperature. So you do want to avoid the sharper edges to improve the heating uniformity. And also you can adjust the electrode curvature and the shape to minimize the heating uniformity. And you can visualize when the product moves in a conveyor belt between the electrode, how the heating pattern develops where the cold spots are. And you could even do some Monte Carlo analysis if the product composition varies and how the properties are varied, and how does that influences the hot and the cold spot location. So you could do the Monte Carlo simulations to identify the effect of various factors. So for those things, you got to determine dielectric properties and the thermal properties for the range of products that's encountered in that industry. The another difference is that like in a traditional thermal processing, you use a typical thermocouple. Because the electromagnetic field is involved, you cannot use a traditional thermocouple. You have to use the fiber optic sensors for the validation. As I said earlier, the validation is purely thermal, so you can follow the same procedures you would follow for the other thermal methods. The key is to identify the cold spot, put the inoculated packages at the cold spots. Dr. Anderson was talking about what are the process parameters you got to focus on. In the RF, it's the voltage or the power level, how much power you apply. You can also measure how much is the forward power, how much power is not absorbed and then it's reflecting back. You want to monitor that. The electrode gap plays a major role. The product geometry, the depth of the product and the sharpness and the shape of the product plays a major role. You could use curvatures to focus the waves towards the center. And the residence time, which is controlled by the bell speed. And finally, the product characteristics. If the moisture content change, how the dielectric properties change, and how would that affect the heating rate and the cold spot location. So these are the different factors you want to pay attention to. So once you do that, once you finalize the process, you do the in-depth quality studies to make sure that the RF process provides a similar or superior quality compared to the traditional methods. So let me go through a case study for the wheat flour. So first what we did for the wheat flour, we wanted to check the surrogate Enterococcus faecium against Salmonella cocktail species. And we looked at the D values at 80, 85, and 90 degrees Celsius at 3 different water activities, 0.11, 0.18, and 0.33. So when you look at here, you see that Enterococcus faecium is more resistant in all cases and therefore is a good surrogate in the wheat flour. And also you can use these D values to identify the different time temperature combinations for the desired lethality you would desire. Then what you do is you go to like a retail packaging type or whatever the final packaging you want to do it, you want to model it across and then optimize the package shape and the electrode shape. And here you can see that the radio frequency, the come-up time is about 8 minutes. The similar one is around 24 hours in a conventional treatment, right? For the same product shape and the configurations and everything. So the advantage of the RF is primarily the shorter come-up time. Then we did the final quality analysis and we showed that it works very well. So just to conclude, the take-home messages are the RF is a thermal process. The primary advantage of the RF is to reduce the come-up time. And that reduced come-up time might allow you to push the temperature higher and shorter time. For example, in the egg white powder, in the currently industry uses 56 degrees Celsius for 14 days. And we showed that the RF-assisted thermal processing can do 80 degrees Celsius for 16 hours. So you can dramatically reduce the time and the energy savings. And because it's a thermal process, you can use the same validation procedures that you would use in a thermal processing. And that's all I have. I would be happy to answer any questions. Yes.
Hi, I'm Dan Castor from McCormick & Company.
Yes.
And I was interested, you mentioned arcing. And when considering, either microwave or RF technology, what's usually the root cause of the arcing, and how does that affect your validation study if that occurs during it?
That's a very good question. The arcing primarily occurs on if there are any sharp edges that will act like an antenna and attract all the RF energy towards that single point. And since a lot of electrical energy is flowing through, it becomes the path of least resistance. And it started arcing and all the energy would flow through. In that situation, you are not treating the other products at all, because all the energy is going to that point. Right. Typically, when the arcing occurs, you would be monitoring it. Typically, you will shut it down, and then you have to restart the process. That's the primary reason for the arcing.
Okay, thank you.